Welcome to the fourth lecture video in our Class 23 series of lecture videos. I wanted to start this lecture video out sort of where we left off in the third lecture video, where we were looking at the hydroboration followed by oxidation of this interesting alkene. We said that the product was an anti-Markovnikov product. It looked like an anti-Markovnikov addition of water across that alkene. But I really wanted to assure students that this is Markovnikov addition, that in this case our electrophile is boron, not the hydrogen atom, and so the boron group adds to the less substituted carbon, generating a carbocation on the more substituted carbon, which can better support that formal positive charge. And then our hydrogen atom adds to that. And since we've formed our carbon-boron bond this way after oxidation, that's where our hydroxyl group goes. And we'll show you the mechanism for this on the next page of notes. Since the OH group ends up on the primary carbon, it's called anti-Markovnikov addition because it looks like it went through the least stable primary carbocation intermediate. However, we didn't, right? I showed you that the process of hydroboration is really Markovnikov. It's just that the alcohol product looks like an anti-Markovnikov addition of water going through a primary carbocation. So recall Markovnikov addition, that's when you add an alkene to acidic water at low temperatures. You protonate the alkene to form the most stable carbocation. In this case, it would be the tertiary one, not a secondary one, and then water adds into that. So hydroboration really is Markovnikov in the sense that it adds the hydride to the tertiary carbon. So, last topic for this video is the mechanism of oxidation. So I said we're using hydrogen peroxide and sodium hydroxide. If we are using those conditions, one could imagine that we have a certain amount of peroxide anion in our solution, and that will add into the empty p orbital of our trialkyl borane and form this borate complex. And now one of these alkyl groups, their ethyl groups in this case, will migrate onto this oxygen and it will kick out hydroxide as a leaving group. Now peroxides are reactive. I know hydroxide isn't a great leaving group, but like I said, peroxides are active bonds, and you can do this 2 more times with the other alkyl groups, and then there's a process of hydrolysis. So with excess water, we simply replace these ethoxy groups with hydroxy groups, and we get ethanol out. So I hope that sort of helps people rationalize what's going on in oxidation. I won't hold students responsible for knowing this mechanism, but I think it at least helps students get an idea of the process by which these trialkyl boranes are converted to alcohols. So with that, good luck on the questions, and that's it for the videos in our Class 23 series.